Okay, so how is everyone today? Good, I hope. Okay. Oh, that's not right. And then we like this better, right? Okay. Good. So, last time, at the end of last time, we were talking about greatest common divisor. Then we hastily wrote down the definition, functional definition of it. Let's write that down again and see if we can understand why it's going to work. So this is a function definition of GCD. Let A and B be in the naturals, and we'll define GCD from naturals cross naturals to naturals as GCD of A and B is, well, the first clause reorders the arguments. So what do I mean by that? GCD of B and A, right? So we'll say that the answer is the GCD of B and A, so by reordering, what I want you to observe is that all that we're doing is switching the order of the arguments. So under what condition do we reorder them? When A is greater than B. So the purpose of this clause and putting it at the top is that in all subsequent clauses we can make the assumption that A is less or equal to B. Okay, that makes that possible. The next clause is the exit clause. So its condition will be in the case that A is equal to 0. So that's the guard. What will be the expression for it? B, right? Okay, then finally, there's two recursive clauses. The first recursive clause is just to make sure that the arguments are in the right order, but the second recursive clause is the one that actually makes progress. So what's the answer? What goes here? So this is otherwise. And what do we need to put here? Well, that's true. That will work, but we can do even better than that. We could say, okay, this will be well, we can put R and A, and then what's R? Right, where R, we're dividing B by A, so this would be B is equal to A times Q plus R. So that's the Euclidean division of B by A. Okay, so let's evaluate this a couple of times. So how about let's compute, so again, we'll take the usual convention, numbering the clauses top to bottom, starting with 1. Let's compute GCD of, what would be a good one? 60 and 28. Okay, so which clause do we find ourselves in? The first clause, right? Because what the first clause does is it makes sure that the left argument is less or equal to the right argument, which is not currently the case. So the first argument, the first clause will say, well, this is the same thing as GCD of 28 and 60. So now, from now on, it will be the case that the arguments are in ascending order. Now what clause are we in? We're going to be in the third clause. Doing that, this will be GCD of, well, let's think about it. What happens is that the first argument, when you invoke the third clause, will become the second argument. So we know that the second argument is going to be 28. So in a sense, 28 kind of just shifts over here like that. And then what's the new first argument? It's going to be 4. Why is it going to be 4? Right. So as an aside, we can observe that 60 is 28. Well, the quotient of that division is 2. And if you have two 28s, that's 56. And then you need 4 more. So that's R. So that gets put here. Okay, now which clause are we in? Which clause do we need to invoke? The third clause again. So the second argument is easy enough. That's just shifting the first argument to the right. Now how do we figure out the first argument? It's going to be 0. Why is it going to be 0? Right, because that's the remainder of 28 divided by 4. So this will be 28 is equal to 4 multiplied by, the quotient is 7, and the remainder is 0. So now this is R. So this is 0. Finally, which clause? Second clause. And the second clause tells us that the answer is 4. So the greatest common divisor of 60 and 28 is 4. Any question about this one? So if the numbers were bigger, you might see some more steps, but you'd have, at least for this definition, you'd reorder the arguments at most once. Then you'd see a bunch of this first argument shifts to second argument, first to second, first to second, first to second, compute a couple remainders, and it actually converges quite rapidly to the answer. So, any questions about it? Okay, so for programming exercises, we implemented this one. Right? That's one of the things for one of the programming exercises. But we also implemented some other GCD functions. One where instead of using remainder, instead of computing remainder, we're just using subtraction. And yet another one where we're using subtraction in some cases, but division by 2 in other cases. Okay, so let's try and justify why should these these things work? Okay. So, and remember the punchline from last time. The punchline from last time is that the word greatest, the adjective greatest in greatest common divisor means greatest with respect to what? Which partial order? The division order, right? The division order. So what in the linear order, the usual order on the naturals, what is the smallest natural? 0 is the smallest natural. And what about the greatest natural? There isn't one, right? Because if you were to say something like, 2370 is the greatest number, I can't think of any number bigger than that. Well, you just take that and add 1, and that's also a natural. So there is no greatest natural in the linear order. For the division order, what is the least natural? What's the least natural? 1. 1, because everything is divisible by 1. Is there, in the division order, is there a greatest natural? It's 0. 0 is the greatest natural. Interesting. Okay. Fine. So let A and B be in the naturals. And so we're going to go through 2 cases. So the first case, in the first case, if A is 0 and B is 0, if they're both 0, then 0 divides A. Why does 0 divide A? Right, because you can say that A, which is 0, is equal to 0 multiplied by 0, or any other number that you like, right? So 0 divides A. 0 also divides B. So what's the greatest common divisor of 0 and 0? 0. So this is the greatest natural. Using the division order. Okay. Second. Well, in this case, we have, what am I trying to say? Let's consider that A is 0 and B is not 0. So in particular, that's going to imply that B is greater than 0. So notice that because of the things we've talked about, the division order before, D divides A for all D in the naturals. Everything divides everything divides 0. As for B, I have a question. Does what am I trying to say? What am I trying to say here? So let's also observe the following. Is this true? 1 divides B. So I'm asking a question now. Is 1 a divisor of B? Yes. Yes, because B is equal to 1 multiplied by what? B. So that's a true statement. What else is going to divide B? Does B divide B? Yes, for the same reason. Okay, so now my question is, does 0 divide B? So again, you've got to carefully think about it. I'm not asking, does B divide 0? That's not the question. The question is, does 0 divide B? What would that mean? Right. So we're asking, is it possible to solve B is equal to some D multiplied by 0? Is that possible? Why is that not possible? Well, because in this case we've said that B is non-zero, right? Yet the right-hand side would be 0. Okay, so this is false. All right. So now here's the question. Using this information, I claim that you can tell me what the greatest common divisor of 0 and B is. What's the greatest common divisor of 0 and B? Won't be 1. It's going to be B. It's going to be B because, well, does B divide 0? Yeah, B divides 0. So B's among the divisors of 0. And what is the greatest divisor that divides B when B is more than 0? It's B, right? So what's the greatest, for example, what's the greatest divisor of, and remember when I say greatest, I mean division greatest. What is the greatest divisor of 20? 20. Does 20 divide 0? Yes. Yeah. What's the greatest divisor of 2370? 2370. Does 2370 divide 0? Yes. Okay, so the greatest common divisor of 0 and B is B. Finally, now we're in the case where neither one of them is going to be 0. So we did the case when both of them are 0. We did the case when one of them is 0. So now let's consider the case when neither one is 0. So suppose that the GCD of A and B is equal to D. So in particular, that would imply that D divides A and what? And D divides B. So it's got to divide both. But now let's write down the equations that this implies. So that would mean that A is equal to some Q0 multiplied by D, and B is equal to some Q1 multiplied by D. That is to say, both A and B can be divided by D. Now we'll do Euclidean division, so Euclid Euclidean divide B by A. So that means there exists a Q and an R in the naturals such that B is equal to A multiplied by Q plus R. And what must be true about R? Zero is less or equal to, R is less than what? A, right? That's all that's saying. That's if you were playing the M&M game and you're trying to make groups of size 10, then when you're finished, the remainder has to be less than 10, right? So if you're trying to make groups of size A, then you can make Q groups, and what's left over has to be less than A. So now we'll combine all of this. Combine A equal Q0 multiplied by D, B equal Q1 multiplied by D, and B equal to A times Q plus R. So specifically what I'm going to do is I'm going to take this formula for A and this formula for B, and I'm going to substitute it into this formula. So that's telling us that Q1 times D is equal to what? Q0 times D. So that's A, and then multiplied by another Q, and then plus R. So now I'm going to isolate R. I'm going to move this one to the other side and get Q1D minus Q0 dq is equal to R. And now what I'd like for you to observe is that the left-hand side has a common factor of D, doesn't it? So we could factor that out and obtain that Q1 minus Q0 times Q, and then times D is equal to R. But now that tells us something about the relationship between D and R. What does it tell us? Specifically, we can say that D divides R. Ah, interesting. So what that's saying is that the greatest common divisor of A and B, where we've said that it's D, it also must be the greatest common divisor of, it must also divide R. So therefore, D, which we said was the GCD of A and B, must divide A, B, and R. And therefore, the greatest common divisor of A and B is also the greatest common divisor of R and A. Interesting. So that's what makes this all work. So I have a question. Really, what this says by itself, this statement by itself, says that the greatest common divisor of A and B should be a common divisor of R and A. But how do we know it's going to be the greatest common divisor? This has to do with how big R is. How big can R possibly be? In fact, it has to be less than A. So here, this is greatest because R is less than A. Interesting. Okay. So now, another property of greatest common divisors that we'll just, I'll just quote from number theory textbook. We won't have time to justify it. Is that this is called the extended GCD. So let A and B be natural, and let D be the greatest common divisor of A and B. Then there exists X and Y, and these can be integers. So again, what's the distinction between the naturals and the integers? Integers can be negative. There exist integers X and Y, such that D is equal to X multiplied by A plus Y multiplied by B. Okay, so then the X and Y pair are called Bezout coefficients. So that's B, E, and then it's got a accent on the E, Bezout. I make no warranty as to whether or not I'm pronouncing that person's name correctly. So they're called the Bezout coefficients. So for example, let's consider something easy. So how about the GCD of, say, 4 and 28? Well, I just want you to tell me the answer. So what would it be? It'd be 4. So what I want you to observe is that it's possible to take 4 and 28 and take some number of 4s and some number of 28s and obtain the answer 4. So notice 4 is equal to 1 multiplied by 4 plus 0 multiplied by 28. Okay, so what I'm saying is that in the previous definition, what would be x?
1.
Yeah, this would be x. And what would be y? 0. So this short example is saying that, okay, the greatest common divisor of 4 and 28 is 4, and the way you could obtain that is by taking one of those 4s and 0 of the 28s. All right, let's make the problem a little bigger. So how about the GCD of 60 and 28? That's what we did a couple pages ago. We established that it was 4. So now I want you to tell me, we should be able to write 4 is equal to some number of 60s plus some other number of 28s. So how many 60s do we need to take and how many 28s? Right. So remember, these x and y, these can be integers. So notice, what if we take 160 and negative 2 28s? That would work, wouldn't it? Okay, now here's another matter we need to deal with. And that is that, yes, I agree entirely that 1 and negative 2 are answers, but here's a different question. Are these the only possible answers? Probably not, because why would I ask that question otherwise, right? Okay, so then notice, furthermore, that 4 could be written as some number of 60s plus some other number of 28s. So what else could we put there conceivably? 2 of these, and how much? Negative 4, is that right? No, I don't think that's right. And I wrote it in pen too. What else would work? Well, how about this? What if we took 28 60s and then negative 60 28s? Wouldn't that be 0? Yeah, that'd be 0, wouldn't it? So if I cross that out and put a 1 there and put a negative 2 there, so it's the same as before. But now let's also take, let's take 28 more 60s. If we take 28 more of them, and then we said, well, at first we'll take negative 2, but how many more of them do we need to take? Subtract 60 more. So we could say 4 is 29 multiplied by 60 plus how much? Negative 62 multiplied by 28. Let's see if that's really correct. So 29 multiplied by 60 minus 62 multiplied by 28. 4. Okay, so, okay, can you see that I made a new solution, right? So from this one, we could add another 28 60s, and we could subtract another 60 28s, and that would be yet another solution. So there's infinitely many solutions to this question. Good. So, any question about this observation? So, in the first place, these x and y, they must exist for reasons that are not too difficult to comprehend, but we're just omitting that. So I promise that they exist, and furthermore, I've demonstrated that they need not be unique. Now what we're going to do is we're going to see how can we compute these with a function. So any question about the task at hand? So we want an extended GCD function. Its signature is, its name is going to be EGCD. It's going to take two natural inputs. It's going to produce a natural output. That's going to be the GCD, but then it's going to produce two more outputs. Where will that will correspond to the x and the y. So where do x and y sit? In the integers. So this will be cross z, cross z. So this one will be a, b, d, x, and y. So we want an extended GCD function that satisfies if EGCD of a and b is dxy, if that's the case, then there's 5 numbers involved here. 2 of them are inputs, 3 of them are outputs, and what equation must all of these satisfy? Satisfies that d is equal to x multiplied by a plus y multiplied by b, and furthermore d has to be the regular GCD of a and b. Okay, so we want a function that will do this for us. Not only will it compute the greatest common divisor, but it will also compute for us the Bézier coefficients x and y. Okay, so the answer is going to look a lot like the GCD that's on the first page of today's notes. It's going to look a lot like this one. But we're going to have to modify it, obviously, because this one is not aware of any x's and y's.
So we get a unique x and y?
So I think there's 2 questions, possibly 2 interpretations of the question. So in the first place, the Bézier coefficients are not unique. So they're just not. So in that sense, it's not possible to get a unique x and y. However, because we're defining it in a certain way, this will give you some specific x and y that work, and you'll always get those ones. So it's unique in that sense, but the Bézier coefficients are not unique, so it couldn't possibly be unique in the bigger sense. Okay, so let's give it a try. EGCD of A and B. So the GCD had 3 clauses. What did the first clause do on the first page of the notes? It reordered the arguments, right? Now, I'd like for you to observe that this output X goes with what? Goes with A, and output Y goes with input B. So we're still going to want to reorder the arguments. We still want to do that. But not only are we going to reorder the inputs, we also need to do what? We'll also need to reorder the outputs. Because if you switch the position of the inputs, then you also switch the position of the Bezout coefficients. Okay. So the guard, to get into the reordering clause, is going to be A less than B, or no, A greater than B. So if that's the case, then the arguments are out of order, and we don't like that. So in this case, the answer would be D, Y, and X. D, Y, and X. And what are D, Y, and X? Where D, Y, and X are obtained in this way. I guess I don't even need the where. EGCD of B and A. So notice that the inputs are reordered and the outputs are reordered. Okay, in the GCD function, what was the next clause? An exit clause. That's a time when you know that we're finished. We don't need to do anything more. All right. Fine. So what's the condition to get in there? Right. If the first argument is 0, then the GCD must be the second argument. Okay. D. Sorry, it should be B. Now the question is, for this one, this is like asking, what is the EGCD of 0 and B? Well, the EGCD of 0 and B is B, and the question is how many zeros do you need to take? And how many B's do you need to take? To get B, right? So we want to find the coefficients x and y. So how many zeros and how many b's? Well, we'll do 0 of those and 1 of those. So do 0 and 1 actually work? They do work. They do work because after all, b is equal to 0 zeros plus 1b. Good. So, any question about this one? A unique answer, yeah.
Unique answer. Why did you pick that one?
Well, it won't be entirely clear why I take it to mean this zero, this first zero, I could have made it anything, right? I could have made it like, I'll take 12 zeros.
Right.
And 1 B. The reason why we're going to take 0 zeros is so it has to be in agreement with the next case.
Okay.
So I can't really fully answer your question until we write down the next bit. Okay. Good. So now we want to figure out EGCD. So in the first place, this is the reordering clause. This is just the clause that says, well, the input arguments weren't in the order that I liked. This is the exit clause, where the problem is finally small enough that you can answer it right now. And now we need to deal with the recursive clause. So this is otherwise. Okay, so we're going to need to recurse. We're going to need to recurse. So in the first place, we'll compute the following. We'll perform the Euclidean division. The Euclidean division of A divided by B. So we'll say that B is Q multiplied by A plus R. We'll calculate that. So that is to say, what we're doing is we're calculating Q and R, because we were already given A and B. So now we're going to recurse. And determine that D is equal to dx0, y0 is, need a little more horizontal space. dx0, y0 is EGCD of R and A. So this is just like GCD, where we're recursing to R and A, except EGCD is going to return 3 outputs instead of 1. Now these 5 numbers, D, x0, y0, the outputs, and R and A, the inputs, they satisfy an equation. What equation do they satisfy? Right. D is x0 multiplied by R. You have to take x0 R's plus what? Plus y0 A's, and add them all up, and you get D. So the recursive call comes back, and now we have this. So what we want to do, we need to take the answers for x0 and y0, and we need to turn them into answers for our x and y. So you can think of it like this. We're trying to compute d, x, and y. So in the first place, we perform a Euclidean division of b divided by a, and then ask someone else to solve a smaller problem. You say, okay, I did a little bit of work, now I need you to get to work. So somehow, magically, they got to work and said, well, I've determined that the greatest common divisor of R and A is D, and the Bézier coefficients in that case are x0 and y0. They were able to compute the greatest common divisor for A and B because a page or two ago we established that the greatest common divisor of A and B is the same as the greatest common divisor of R and A. So D is right, but x0 and y0 are not the Bézier coefficients we need. We're going to take these two equations and we're going to combine them. So in particular, what we want is we want to substitute. We want to, in the first equation, solve for r, and then plug it into this equation. Put it right there. So that would tell us that d is equal to what? X0 multiplied by b minus qa. And then plus y0 a. Now we want to take that last equation and we want to rearrange it so that it looks like something times a. The right-hand side is what we want to rearrange. We want to rearrange it so that it looks like something times a plus something times b. Okay, so let's multiply it out and collect like terms. So this would be x0 times b minus x0 times q times a plus y0 times a. So now, only that term, only the first term has b, and notice the last two terms have a factor of a. Okay, so in that last term, let's factor out the common factor. So that would be d is equal to x0 times b, then I'll say plus something times a. What goes in there? y0 minus x0q. And I claim that you can now tell me what the Bezout coefficients are. So what are they? So which one is which? So we want an x and a y. What's x and what's y? Right. This one is y, x0, and x is this one. Because have a look of the form that it's in. We're saying that d, the greatest common divisor, is obtained by taking that many a's plus that many b's. So, after all of that consideration, we can finally write down the answer. The answer is d is the greatest common divisor, which was provided to us by the recursion. The recursion also told us the Bezout coefficients corresponding to the smaller problem. Then we turned that answer to the smaller problem into the answer to the bigger problem. y0 minus x0 q is x, and x0 is y. Amazing. Good. Any question about this definition? That's more complicated, huh? So let's see if we can work one out. So any questions about the definition? Okay. So let's find the EGCD. Let's evaluate EGCD. EGCD of, well, let's start out simple. 4 and 28. And we're going to do it with a table of values. So in calculating this, notice that there are, how many different values do we need to keep track of? Well, there's 2 inputs, A and B. There's 3 outputs, D, X, and Y. There's X0 and Y0, those are intermediate values, right? Those are outputs from the recursion. And we'll also need Q and R. So AB, DXY, X0, Y0, Q and R. Whole bunch of things. Okay. So let's make a nice table. No, A. Right, A first. A, B, D, X, Y. The next thing that we compute is Q, R, and then we ask for the recursion to get the Bezier coefficients, X0 and Y0. Okay. So at the present time, we've just been asked to compute EGCD of 4 and 28. What is it that, of all these quantities, what is known? A and B. So 4 and 28. Now, if you look at that, at the definition, then this would be the first clause, the second clause, and the third clause. Well, we're in the third clause, which means that the first thing we need to do is compute the quotient and the remainder. So what is the quotient and the remainder of B divided by A? 7 and 0. So somehow we do that, we determine the quotient is 7 and the remainder is 0. So now we're going to recurse to a smaller problem and say, okay, I've done a little bit of work, I've computed the quotient and the remainder, and now I'm going to ask someone else to compute what? We're going to ask them to compute the EGCD of what? Of R and A. So now we're going to compute the EGCD of R and A. R is 0 and A is 4. Well, this computation has no idea of any of the things occurring up here. So it comes into existence with a blank slate. So you've got to make a new table. A, B, D, X, Y, Q, R, X0, Y0. At the present time, for EGCD of 0 and 4, what is known? Right. A is 0 and B is 4. So those are the two inputs. Now, which clause will we end up evaluating? The second clause, right? So the second clause is evaluated. We determine immediately that what's the greatest common divisor? 4. So this is 4. And then what are the Bezout coefficients? 0 and 1. Because what we're saying is to get 4, we're going to take 0 zeros and 1 4. Okay. So now, the recursive call returns. The recursive call returns, and the answer to the smaller problem is established. We're saying that 4, 28, the greatest common divisor must be 4. But then, where do this x and this y go? Right, into x0 and y0. So this is 0 and this is 1. All right. So that's x0 and y0. So the answer to the smaller problem we've written in red. We computed a Euclidean division, found Q and R, asked someone to solve a smaller problem. They returned to us the answer 4, 0, and 1. Now from those, we can figure out the answer to our question. So in particular, we want to compute the answer, we want to compute x and y. So 4 and 28. The greatest common divisor is 4. But now, how do we compute x and y? What is the formula for x? Right, it's y0 minus x0 q. And what's the formula for y? It's just x0, so that one's pretty easy. So y is just x0. So that would be 0. And I already forgot what the formula for x was. Y0 minus x0q. So that would be 1 minus 0 times 7. So this would just be a 1. Terrific. So the answer to the question is therefore equal to what? 410. Okay, any question about this one? So I gave us a problem that required just one recursion, right? We just had to do this table and then recurse to 1. But in principle, it could recurse to a multitude of such tables, and you could carefully calculate each one. Okay, so that's all for today. Have a nice Thursday.